Okay, hello. I'm going to do another quick sample lesson um, because I have a little bit more freedom over my body. And look at this, I actually have pretty good working fingers. They only go out so far, but I'm working on things. Um, so I'm going to do a quick lesson on the formation of solar systems. Just kind of a simple, brief overview. I'm not going to get too into details, and we'll see how it goes. Okay, so we're actually going to start at the end with a supernova. So a supernova is an event where a star explodes. It's the end of its life. The inward crushing pressure of its gravity and the outward radiation pressure of its heat fall out of balance. It's running out of fuel. And the balance finally comes to an end. This only happens with very large stars. And it eventually explodes, expelling all of its shit outward. And during that explosion, there is a lot of pressure in the core of the star and in the inner layers of it. And that pressure plus all of the heat creates kind of the heavier elements, the stuff we know and love. We have oxygen, carbon, silicon, aluminum, all that, uranium, all the fun stuff. Because stars, when they are burning and when they're shining, are primarily hydrogen being fused into helium. But anyway, at the end, they explode and they expel all of their stuff that is inside of the star and any planets that are directly around them will be expelled as well. Kind of, blown to bits. So all of those bits drift for a long time, cosmic long time even. So sometimes millions of years, and as we know, everything with mass has gravity, and everything with gravity attracts other things with mass and gravity. So you end up with a nebula eventually. Nebulas are really just large, very large, usually a few hundred light years across, collection of shit from exploded stars and failed planetary systems, even failed stars, but they are the birthplace of new stars. So you've probably seen this picture before. It's a pretty famous one from NASA of, you can see new stars being born here. So at the beginning, there is a nebula and there is a lot of stuff here. And all of that stuff kind of starts to come together. Let's move over to create a protoplanetary disk. So you would have some of the lighter gases and some of the lighter elements, maybe some. We're not going to get too into detail there. Let's just say we're going to call it that it's just the lighter gases for simplicity's sake, because that is what most of it is going to be. They're going to start coming together and crushing together and heating up. And once you start getting high pressures and high heats with a lot of hydrogen and helium, you start to form a star. Sorry. So it starts to heat up and it starts to grow. And because it's heating up and it's growing, it is both exerting pressure outward due to the heat pressure and the radiation pressure, but it's also pulling things in from outside, like what you have here. You can see that there's a lot of stuff being pulled in around it because it's growing in mass, and thus it is exerting more gravity. So you start collecting up elements that end up kind of becoming a ring around it. I've heard a lot of times people's question is, how come solar systems are always kind of flat rather than being a sphere? And I don't know where I put it. So as things start to try to go in toward the protostar, they are pulled relatively linearly. Well, not even relatively. They are pulled linearly toward it. But there is always some sort of angular momentum going on, and that momentum is conserved. So when everything starts to grow smaller and it starts to form this protoplanetary ring, those angular velocities, it's like a ballerina with her arms out, and then she pulls them in and she starts to spin faster. So the closer you get to the star, the more that spin is, and the more backwards you would have to go to overcome that spin. Oh, I guess backwards. You would have to go to overcome that spin. Go away. To overcome that spin. So most things end up actually missing. So because they miss, they go around, but then they're pulled by gravity and they keep going around, and that forms this ring. And now that happens in all directions, but because the forming star was already spinning, that is influencing the direction, not slightly through like relativity, but mostly just due to conservation of angular momentum. And things kind of crash into each other and rub up against each other and slam until kind of whatever orientation the main body was spinning is kind of the way that everything ends up spinning. Let's see. This is it's also an accretion disk, like what happens around a black hole. That's probably where you would hear of an accretion disk more often, is around a black hole, where you have kind of all the stars and the hot plasma that's surrounding it. The same thing happens here, just on a colder and smaller scale. So we're already on 3. How about we go to 4? So as time goes by, the star is exerting pressure, and all of the stuff that we saw in the ring that's behind me starts to kind of bump and smack into each other, and it starts to grow. And it's kind of a positive feedback loop where as it grows, it gains more mass and more gravity, so it grows faster and it grows bigger. And that's when you start getting planets to form. Sometimes you'll get rocky planets, sometimes you'll get gas giants. Rocky planets are obviously formed mostly from heavier elements, things like your carbon, your silicon, iron, things like that. And then you have your gas giants, which also do have those heavier elements inside of them. They're just all kind of slammed down to the core, surrounded by the gas. So things start to slam into each other and rub into each other, and they clump up and they start to form these mostly spherical balls that keep growing as they keep encountering more stuff that gets attracted to them. And so each of them kind of clears out its own highway through its new made orbit, collecting up all this stuff around it. Which one is it? Oopsies. So as planets are forming, they're collecting up a bunch of crap, and all of that friction and internal flow and the elements and the heat pressure from the sun make it real hot. So almost all rocky planets will be born pretty molten, like this. Our Earth looked like this once, not very inviting. And the fact that they have no atmosphere or no magnetic magnetic fields, sorry, protecting them from the sun's rays and cosmic wind and things like that. It just kind of adds to the problem, and they continue to grow and they continue to be hot. But this is very important because as they're so hot, it kind of allows things to separate out. The heavier elements fall down and the lighter elements kind of rise to the top, just through density. So you end up with things like our Earth and its mostly iron core, iron and nickel and, its metallic core. And then outside here on the surface, there's some lighter things and also, our atmosphere. And during this process, there are, all sorts of elements. Everything is here. It's just all being, crunched up together. And there's going to be some water here too, but it's going to be too hot for it to survive, obviously, in liquid state, and a lot of times too hot for it to survive even in its gaseous state. It's going to evaporate off and kind of just be lost to solar wind. But luckily we have comets, small inlay, very professional, terrific. They are often very icy, and they will slam into the planets, bringing water, continuing to supply them with water. This cools them down, but it's negligible. But what's more important is that they continue to add water, and that water does dissolve some of the elements that are in this magma hellscape, and that starts moving things around a little bit more than just melting and density can. And so I'm not going to go much further here. This is the basics of how a solar system would form, with a focus on rockier planets because we live on one. So if there are any questions, let me know. I know it's not very in-depth, but I did this less for the lesson and more for testing and making sure nothing goes too horrifically wrong. And it seems to have all been mostly fine, but I'll have to watch the video. Okay, love you, bye!